Yes, good morning, everyone. Do you hear me back there? Yes, thank you, thank you. So, most welcome to this morning session. And I think the title was Everyone Wants a Digital Twin. And I think that's pretty much what we experience these days. So, we're a team that will present the advancements of a lab development. I will not talk much. Jannike is the project leader for a project called Digilog, which has been the main drive for this development. We have Masoud here, and Wajid and Guyong is actually down in the lab, just ensuring that the technologies are working, but they deserve a lot of credit as well. I will take just a few. This is what we'll talk about. I have a few minutes of introduction, but then Jannike will talk a little bit about the digital twin, and then Masoud will introduce the testbed that we have, and we'll try to hopefully get some demonstration to work. You know how it is, but let's cross our fingers. I would like to spend just perhaps 2 minutes on the research environment that we have here at KTH, because we try to collect all the research groups on one day. So if you have the chance, there is a program in this room all through the day to follow different sessions. And the groups that we have 3 research groups, and the team that is presenting this one is within production logistics. We have a research team on production management later after lunch. We have a research team on strategic maintenance that will have a session at 11. So please welcome, and this is the 3 profiles that we have here at KTH Södertälje. We're a growing team. We started off, I don't know, 3 years ago, perhaps, something like that. The first of us came. So it's been a rapid growth during these years, and yeah, I won't introduce them all, but some of them you will recognize from this session. As I said, during this Thursday, we will have this focus on the 3 teams. I would also like to invite you to the open lab. During lunch today and lunch tomorrow and 2 o'clock, I think, tomorrow, the lab will be open downstairs, and there will be demonstrations every half hour. So if you have the possibility, you can hop in there. Yes, apart from that, there's a lot of nice sessions. Lean Center has their whole day tomorrow. But today then, if we focus on the research, this is the agenda as you see for the day, and this is the session when everybody wants a digital twin. So the 3 teams will present different aspects from different projects during the day. And I think you will introduce what projects contribute to this session. So by that, most welcome, and I'll hand over to Jannike.
So now you should be able to hear me. So I thought I should start a little bit about What is the digital twin? Because there is a lot of different discussions about when we talk about digital twin, which everybody wants to have, we have different opinions on what that should actually be. There are around 40 different definitions of a digital twin, which shows actually the broad spectrum. I selected 3 of them, which fits quite well into what we are doing. So I selected one from Glaskin and Stagel, which tells that a digital twin is integrated physics multi-scale probabilistic simulation of an unbuilt vehicle or system that uses the best available physical models, sensors and updates and fleet history to mirror the life of its corresponding flying twin. That is, as you see, since it's a flying twin, it's from the air industry, but you can also use the similar one for logistics with some modifications, which I will come back to afterwards when I talk about the challenge, and which you will also see when we have the demonstration by Goyong and Vaid later today. We also have that a digital twin is a high fidelity representation for operational dynamics. It should be the physical counterpart, and there when we talk about the physical counterpart, we have the problems with the modeling already in having the physics. For instance, if we use Unity, as you will see that we have used later, it's not so easy to get it in there. But it can also be a digital twin, a set of virtual information that constructs and describes something. That is what you often use in the product development part. And in a lot of cases, that is also sufficient in the production logistics part. So this is the background of what we're doing when we look at what do we mean with a digital twin. But for the daily operation, we normally use for our lab some short connections, where we just say that our digital twin can mirror and simulate complex scenarios very close to the reality, and we can use it for different things. However, when we say close to the reality, that is where we start to do the modification and the reduction of the complexity. If we use it for simulation, we will have to look into the granularity of what we're actually looking for. If I have a digital twin and I want to investigate how a robot is moving, then I would have to have a very much more detailed digital twin than what I'm normally looking for, which is the flow of material, where I can have a quite high level digital twin. That is what we will see today, but where I still can get the information out. But that also means that if I have designed a digital twin for something, I cannot just reuse it for something else. And that is very important because it might not be valid. We come back to that when we look at what we use our digital twin for. But we can also use it for monitoring. You can see it for, that's operational maintenance, for instance. You can use it if it is connected, if it is sufficiently real. We will see today that we have the possibility in our digital twin to start it remotely. And that is where we, for instance, would use it for control something happening down in the lab, because we could do that from a different area. So there we can do it both for controlling and for monitoring. We can also use it for learning. That is where you see it more and more application, actually. We use the digital twin for learn something about the system, specifically before the system is in operation, or for teaching purposes. If we do not have so much equipment, we can use VR and AR to get a very realistic view. We can also get an interaction with them, depending again on the physics. There it is very important how the physics is in your digital twin, that it's similar to what you actually do if you train something for operation. You also have to have the physics and the movements correctly modeled in the simulation. So, but for instance, we use it more for understanding the system context, and then we can use a high-level digital twin with just the basic information in it. But it can also support introduction of the new technologies. That's a little bit what Masoud will talk about in our test beds, because there we want to test them out. We have the opportunity to try them in different ways. I'll come a little bit back to that when I say talk a little bit in how you can use it for planning purposes and how you can use it for operational purposes and some of the limits of that. But even though everybody wants a digital twin, it is not always that you can get so much value out of your digital twin. That depends very much on which data you put in and also what you want to use it for. So what we sometimes see, if you look into the literature and also if you look at a lot of the companies who's invested in building a digital twin at a time, they're like, if you look into IoT, they're not always prepared for what it should be. I've taken a photo picture here where you see the additional value. If you have a non-organized or low-organized chain where you do not have access to your an unstructured and you do not have very much access to data, you will actually not profit very much for the of your digital twin in an operational phase. You could still use it for teaching purposes. So if you have to learn your or to teach your or train your operational workforce, you could still use it at this level. But you wouldn't have the main advantages as you will have if you go into the maturity, which is the optimal one. You see, the main problem with the unstructured is that we do not have data access. It means what we simulate is not sufficiently relevant or near to the reality. And that is a big difference, danger, because every time we then make a decision, we can also then have a problem of making a decision on the wrong permissions, and that is not very good. So also in the execution, you see that you have no sufficient data, and you will actually not have access to the historical data. That doesn't mean to be so wrong for the execution if you look into new technologies, because there you cannot use the historical data anyway. That's because they might not be valid. But if you look into the defined one, we have the failure prediction, where we can use it much more. There we would have an advantage of having the possibility to look at it afterwards, analyzing it in more detail. And for the planning, well, you can change the phase. You can look at, for instance, as you see, I've taken this from the maturity of, again, from the digital twin of the airplane industry, because they are quite advanced in this way, and they had a long experience in using digital twins. But in the execution, you see, again, we do lack the historical data for actually doing the calculate, so we would not use that for the operational, but we could use it in the planning phase. Then we come to the optimal phase, which is where we would like to come at the end, where we have fully access to all the data, we have all what we need. That is what we will see how realized in our test bed down here, which we will see afterwards, where we do get the data. The only big challenge with that is, of course, we have a test bed and we do not have a very structured collection of data at the moment, and how we can analyze the data afterwards. So in the service development, what do we do with all the data we collect? There we have to develop more services, and that's quite typical. But if we now go to how we could use it in more detail in the planning, it's mainly help you very much to understand the better what you're looking at, the system context. When you want to involve something, because you can actually move these very detailed and look at one slot, what's happened in the digital twin several times. You can use the replay function, and then that will help you very much to understand a specific problem if it is modeled. It's always if it is modeled, that is very important. That's why most of them are based on the simulation. We will see some of that. And it will also help you to better understand the prediction on what will happen if you introduce new components. However, also there, it is important that it's sufficiently well modeled so that you can do that. You can also test the behavior of new components. In different environments, you can change something, so you can change the conditions and see what's happened. Again, that depends on what sort of algorithm you have used for your movements of moving objects, for instance, in your digital twin, how precise or how similar they really are to the real world algorithm. And again, as you can see, we can only actually investigate what we've modeled. And there again, we can use a granular approach so that we can actually change the granularity of our simulation model depending on what we're looking at. We will see that in 2 slides. In the operative process, we can simulate how it's actually running. We can import the data if we have the data access, which we have here, for instance, to exactly see if what we expect to behave in the planning, also behave that in the operational phase. We can investigate specific problems, which we cannot, for instance, if you look at maintaining and you look at an offshore maintaining, it's often not possible for us to go there to investigate the problems, but we can use the digital twin to understand what's happened if we have sufficiently number of data there. And we can also use, well, here for that we use the simulation algorithm, at least for us in the moving objects, in the production logistics, and that might not really correspond to the physical object. That is what we will see here. Here we see, this is modeled by FCC, which is the Fraunhofer Chalmers. It's our AGV. It's the old AGV. We now got a new one. But it's calculating how it moves in our lab, so you will recognize that when you see the digital twin. And this has a quite optimal algorithm. So every time when I look at how it moves and calculate how it should move, I would use an optimized algorithm. However, that doesn't mean that that is what my AGV shows me. So we here see that this is from our lab. You will see the live demo later. We have made a spaghetti diagram, or Vaid made a spaghetti diagram. You see the same environment, and you actually see the same, you see the same AGV or a similar AGV moving around. And if you look at what it did here, that is a predefined route, so it's moving a little bit different. And if you would then compare with the same optimized route which we have from FCC, you will see that there will be a difference. And then the question is, do we want to optimize how the AGV would move, or do we want to optimize that our digital twin behave, also the AGV in the digital twin, an AGV is an automated guided vehicle, how that move so that it gets as close to the reality as possible. That is two different approaches, and we would use the different approaches depending on what we are interested in investigating. If we have access to the AGV algorithm, then we might try to optimize the AGV so that it will be more efficient in the future. However, in most cases, we do not have the access, and we do not get the information either from the producers how it calculates. So then it would be, in order to make a more realistic forecasting or a more realistic way of investigating the problems, we would try to change the algorithm which we have under control, which is the one which we have used for the theoretical calculation, the optimized one, and then make it less optimized so that it fits to the reality. Because at the end, what we want to do with a digital twin is to solve a problem, and we want to solve a physical problem, and that is mostly based on the reality. So if I cannot change how my AGVs moves, I have to adapt my digital twin so that it fits to the reality and not vice versa. So here you just see a second example. It's exactly the same example, but what I wanted to show here is that we can change the perspective, so that will also give us an opportunity to look at it in different ways if I want to investigate something. Here we can of course make a replay of it, and then I can, for instance, detailed look at how does this move, because this is from the reality, so that is how it exactly moves, which I need to understand and analyze in order to be able to change the digital twin later. It seems that digital twin, since everybody wants it, is a very good way of doing it. But as you see from the list, we have a lot of challenges. Some challenges are more detailed or more severe. Some we have already solved. If you come to the security, for instance, we have already solutions, so it's not a big issue anymore. But if you, for instance, look into the data acquisition and thinking of, if we want to use it in the planning process, where should I get the data from? I don't have the real data because I want to do it before. So that is one. How would you want to model that? The second one is you often have to do then manual data acquisition, and that is very time consuming. That is, again, depending on the maturity of your company, which you saw in the beginning, where I had these three where you can profit from your digital twin. And we have a lack of standardization. You see that quite easily when you look at the 40 different definitions we have of a digital twin, and that also that we do not have a specific standard, so we cannot read. That is also because we use it for a lot of different things. So it's not always about that we do not have a standard. But the more important thing is the accuracy. It is, even if we have accurate data, it's not so easy to get the digital twin to exactly doing the same. And that means that every time we make a decision based on what I've seen and analyzed in my digital twin, I have to take that into account. That is the same as if you look into simulation models. So it's not really very much difference. And for a long time, you could also see that a lot of the simulation models, they are quite similar to that. Another very important issue is actually who's owning the data and who's getting access to the data and what can you do with that. I said that we have the possibility to collect, but we are not so far now that we have very good ways of visualizing what we're collecting. That makes it very difficult for us to analyze. So that is two of the things we are working on. We're also working on the digital twin modeling. So I will just, before we give further to Masoud, I would just say here that you also have a digital maturity continuum where you can see where you can use it. The operational technology world. Now, we would of course like to come into the prediction area, and we would like on the other side to get autonomous decision making, specifically in logistics, where we look a lot into automation of the processes. So there we have also, in order for you to check if your company is ready for your digital twin, there are some questionnaires around where you can check if you will actually get enough out of it in order to support the, to afford that you have to invest quite much into that. So that was all for me. And then it's your turn.
Do you hear me now? Yeah, okay. I will talk a bit about the associated projects that we have, that how digital twin and the testbed can help these projects to achieve their goals. Apart from the first three projects, CPALS, LOVIS, and Digilog, Unilog is a project that we use for the educational purpose. And I can say the testbed that we have developed here is going to be used for students to learn stuff and practice and have a hands-on on development of digital twin. We have a vision for this testbed that we have developed here at KTH, which is also combined with the testbed that we have at Scania and is under development for AstraZeneca. The vision is that we want to have, as you see, a physical production logistic flow as a normal situation, and create a digital twin within a cyber environment, which is exactly the mirror of what happens in the reality within the physical environment, and tie these two environments together through real-time data. So we fetch data in real time and send them to the cyber environment, analyze the data, and then get the application we want and send it back in form of support for decisions to the physical environment. So by this way, we can plan and optimize what we want to do in real time. So instead of sitting and simulating and see what's the best option, we do that in real time. And that's the vision. When it comes to a practical project, we have one example, which is LOVIS, visibility in logistics. As you probably know, the level of visibility in logistics is usually lower than manufacturing. So it's really important to know what exactly is happening, especially when it comes to the interface with inbound logistic and outbound logistic. So we need to understand internally how transparent the system is for itself, how different persons, different systems, different part of the organization know that what exactly is happening and why they are happening. And then when we talk about the supply chain, about the cooperation with the retailers and suppliers, still the same question. The suppliers are keen to know that what happened with my customer, and the retailer want to know that what happens with my supplier. When I get the parts, how can I get them? What is the quantity? What is the time? And so on and so forth. So if by having a digital twin, by having a smart model behind the whole processes, we can support this to answer these questions. This is another example from CPALS project, which is a joint project between Sweden and South Korea. The aim for this project is, as you see, to create a platform for cyber physical assembly and logistics system. Cyber physical was the vision that I showed you, that it has the physical flow and the cyber flow, and that is connected together through data. So here, as you see, we have a dedicated module for digital twin and advanced analytics. So it gets the data from sensor data, the instruction of the work, the operational data, and then do all the simulation and all the simulation and advanced analytics in that module, so it can support the whole system. As you see, because it's a bit broader project and it's not only about logistics and assembly is part of it, so we need to have more type of systems like the MES apart from the ERP system. So we can get the data from the manufacturing as well. For Digilog, which is the project that I mainly worked on it, we have developed an environment so we can test different type of scenarios for digitalization of internal logistic activities. This has been done with in cooperation with our industrial partners, AstraZeneca and Scania. But if you want to ask, okay, where should we start? First, we need to have some technologies that enable us to develop the work. I mean, after we know what we want to do and we have all the theories. The first technology that we have used is a collaborative robot from UR, which is called UR10. These robots are, compared to normal industrial robots, which are very heavy and dangerous to work, are designed to be cooperative for human workers. So you can work beside them and then they're supposed to help you. For instance, if you go too close or if you touch them by accident, they will stop working. So it is said that it is designed to be 100% safe for human, although there are some challenges still that needs to be solved. For the AGV, which is automated guided vehicle, it's kind of old technology, but has a new generation, which is autonomous driving. For example, this type of AGV that we are using is a MIR 200, able to carry out 200 kilograms around. And one specific specification of this type of AGV is that they are able to avoid obstacles when they see obstacles, try to move around. The other technology that we have used is the smart camera, which is completely critical to have digitalized and automated system, because we need to have many different sort of vision system to be able to get the data and see that what is happening. The next technology we have used is VR and Unity modeling. Unity is an engine to create games that we have used here to create our digital twin model in 3D. So basically you can develop any environment you want by using Unity program. And if you combine it with VR, then you can see the reality, the virtual reality by using the VR glasses. And then we have the RTLS, which is real-time locating sensors. This technology, this picture is not so big, you can't see the details, but it has some sort of sense points that you can place around the environment that you want, and you have some sort of tags that they can track these tags in real time. It's very much like internal GPS, if I want to say. Quite helpful and useful if you want to have a control over your flow in the production logistic. But then when we say that now we have collected all the data from the physical devices, it's time to ask how to manage this data and how to stream this data. And there we decided to use a streaming platform, data streaming platform, which is called Kafka Apache. I will explain shortly about how it looks like. And then how to manage the orders. We use Node-RED, which is a visual programming programming data platform. For connectivity between the devices, right now we are using Wi-Fi, but we plan to move toward 5G, which we think is faster and more stable. Here I have two films, hopefully they work. Before we start, we can imagine that how a production logistics system looks like today when it's not automated, and compare it with a situation that is digitalized and automated. This is an example of kitting process. So as you see here, the operator gets a manual, try to read it and understand what parts should be kitted for the next production. So he pick the parts, put them in the box. It's a bit exaggerated, but just want to show that it has some physical work. So he had to move everything around, physically push the button of the door, hold them themselves. And here, since we have elevator and we want to deliver the parts to pedal car factory that we have on the second floor, so he has to go through the elevator and do all the works manually. Probably even he needs someone to hold the door for him. Now we can see the digitalized version, which is kind of a vision for us. As you see here, the operator now is controlling the process instead of doing all the manual work. So the UR collaborative robot, which is standing close to the operator, doing the kitting, the AGV, which is responsible for transportation of the material, is called by the robot that now I'm done, transport the parts. So now you see the AGV talk to the door, open the door autonomously and do the same thing with the elevator. And finally do the same thing with the door of the lab. There are some fake stuff in this movie, but this is the vision that we want to have. Yes. About creating the digital twin, as you saw, we have the physical system there, now with the technologies that we thought might be useful. And we want to create the digital twin of it. So first we need to do the modeling. Within the digital twin, we need to define what are the objects that needs to move around. For example, walls, probably we don't need to do, or the pillars or some other stuff. But the AGV, the robot, probably even the racks that we have, we might need to create them in a dynamic way. Then we need to connect these digital objects to the physical ones, and the whole model should support the system by sending the rapid decisions. From the physical side, we need to get the data in real time. We need to connect them to their digital twin, and then receive the feedback from the cyber side or the digital twin. That's also in real time. This is, as I said, shows the example that when they want to collaborate with each other, this is the question that the UR robots needs to know: when does the AGV arrive, and the AGV needs to know when does the robot finish the job. So instead of scheduling everything, we let everything happen on real time and make the collaboration and scheduling based on what the situation is. About the data streaming architecture, as I said, If we compare with the traditional way of connecting everything together, let's say we have RTLS, we have the AGV camera and robot. If we want to connect them together, then we should do a peer-to-peer connection, which is really complex. If we want to add new technologies, we have to repeat the same process again and again. And if we want to remove something, then we should be careful that what is still in that place that not hurt the whole system. So instead, there is a technology called Enterprise Service Bus, which is dedicated to help the system that the data go through this channel. So we just need to make interface or program the interface towards the Kafka. So we connect everything to Kafka, and then the data, let's say from the AGV, goes to the camera and to the robot, even without sending this data exactly for camera or for the robot. But the data will stream through this Kafka server, and the robot and camera that needs that data will consume it. For later use or for later analysis, we are even able to connect this Kafka server to database. So we can keep a history of the data and then use them for later analysis. And then came this question, how should we tell the object what should they do? And that's the question that we can solve by using application that we call it Digilog Manager. We are developing it. And that's where we use Node-RED, which is a kind of a simple interface for programming. In terms of connecting the devices to Kafka, we have used the RESTful API to get the data and to get the data from the devices and post the data from the devices to the Kafka. And here you see that we have the manager that manages the stream of the data. And as an example of the applications, you see that we have real-time data analyzer. For example, we can have dashboards, we can have logistic heat maps, and we can have real-time 3D models. So we see in real time where in the lab that we have the highest density for the movement, or if where we have accidents, where we have lots of inventories and so on and so forth. So depends on us. Yeah, now I think we can switch to demonstration. I have Wajid and Guyong downstairs connected through WhatsApp. So, hello Wajid. You hear me? So, let me just switch to just a few seconds. So now we have you on Twitch. Yeah, I keep you on the mic so everyone can hear you. You can explain.
We have two robots, one universal robot, and we have AGV. We have a vision system up there. It's not mature enough, but we are working on it at the moment. So I will give you a demo. We have this object, which is the algorithm is trained to recognize this object. I will briefly minimize this window and try to recognize this object from the camera.
Have 3-second delay from Twitch. So what's happened in the digital world is ahead of the reality.
So the object has been recognized. There is a bit of latency. The universal robot will pick up the signal from the computer, from my program that I have written, and start moving. And before it moves, I will click the button to call AGV to pick up the box. So as you can see, the UR robot is moving, and you can see the same thing in the digital twin as well as in the real time.
This situation represents that the UR robot picked a box, placed it on the AGV, and the AGV delivered to the next station, which can be quality control, or which can be a place for that another operator puts an object inside the box and deliver it to the next destination for the AGV. So as you see here in real time, you get the spaghetti diagram on the digital twin. Just to give you an example, if you stay in the middle of the way that the AGV is trying to go, you get another type of spaghetti diagram, and then later on you might be able to analyze why this happened. And imagine that you are working in a real situation, that you get lots of this type of deviations. So finally you realize that, okay, this operation is supposed to take 10 seconds, but now it takes 12 seconds instead. It's because I have lots of obstacles in the middle of the way. So how can I plan it in the future? Okay, thank you so much. Yep, thank you. Yeah, I think that was all we had. So please, if you have any questions to Jannike and Magnus. Yes. Can also add that now that we see AGV and the UR robot were the two main players in this scenario, the AGV connection was much easier because we could use the API directly from it and then connect it to the model. But for the UR robot, we were not able to do it, so we had to use the socket connection. It means that if we want to change the program of the UR robot, we have to do this type work manually for the robot itself. So we have to have same program in the digital world and in the physical. But for the AGV, you just model it in the 3D model and then it's done. More questions, comments? Not yet. Yes. Yes, of course. It's one step that we need to solve. Yeah. Yes. I think Yannick mentioned about the granularity of the model, which is very much depends on what application you want to get from the model. If you are just interested to see the behavior of the movement of the objects around, then probably you don't need to have very precise modeling. But as you said, you see the blue box that we put on the AGV, sometimes it's on the corner. Then it's a matter of safety, that it might collide somewhere or had accident. Then we need to be very precise from the beginning that the blue boxes or whatever we put on the AGV should be exactly as what it happens in the reality. So we don't model something wrong and then get a result that cannot be used in the reality in the future. More questions? No? Okay, thank you so much.